Okay, so with this lecture number 8, I guess, we will conclude our investigation of Markov chains, or our first exposition to the theory of Markov chains, which I hope you enjoyed a little bit. And we will conclude our journey through Markov chains with the theory of electrical networks. So it's just a network of nodes and wires which have conductances, and as it turns out, you can give a nice probabilistic interpretation to those quantities which appear in the engineering theory of electrical networks. So we can find a lot of very nice and intuitive representations of quantities which appear in electrical circuit theory through a random walk on the corresponding network, which is then determined by the features of this network in terms of conductances or resistances and so forth. And this is, in its own sake or in its own thing, already a very nice theory, but we can also use it in order to give a very nice kind of recent, like 30-40 years old recent result about the characterization of recurrence and transience of what is called reversible Markov chains on such networks in terms of the existence of finite energy flows. And this is a very powerful criterion which is very useful for the analysis of recurrence and transience of Markov chain independent of the physical connection. And we will give an example to this. So this beautiful application of random walk theory to the case of electrical network will be the conclusion of our investigation of Markov chains. And after that, we will make a step towards the theory of martingales. Okay, in lecture 8, we will complete our introduction to the theory of Markov chains, and we will do so by discussing the example of Markov chains which appear in the theory of electrical networks. Electrical networks as they appear in engineering and so. So an electrical network, just before we give a formal definition, is a graph effectively. So it's a collection of nodes and edges, and these edges, they are all endowed with a certain capacity or conductance, as we say, C, which is the conductance of that particular wire, and the inverse of the individual conductance of a wire is also sometimes called the resistance. So basically we have a network of nodes and wires where each wire has a certain resistance. And mathematically we define this as follows. So an electrical network is given by a collection of points or vertices or nodes, which is countable. And then we have a resistance function, which for every pair of points ij in the network, or each pair of nodes, associates a certain resistance function, which is symmetric, which is the resistance of the wire which is installed in the network between node I and j. We say that the resistance is infinite if there is no node at all, and otherwise we say that that these two nodes are connected by an edge. So effectively, this resistance function singles out certain connections with positive and finite resistance. These will be then the edges, the actual wires, everywhere where there is no edge. That's indicated by the fact that the resistance between the corresponding nodes is infinite. And we say that the network is connected if for every possible choice of nodes there is a sequence of edges which connects them. And as we have just said, we also talk about the conductance, which is just the inverse of the resistance, so of that corresponding wire or edge. Also, the conductance function, therefore, is a symmetric function. We also want to assume that if we fix a certain point I or node in the network and we take the sum over all other nodes or all nodes in the network of these conductances of all the wires which have an endpoint in this single position I, that this sum, which we denote by Ci, is finite for all nodes in the network. If this is the case, then we can introduce the Pij collection of numbers, which for every pair of nodes ij is just the normalized conductance which connects the nodes I and j. The normalization is done by dividing exactly with this number Ci, which is the total conductance of the individual node I. And this Pij then will be, by definition, a stochastic matrix, which is a Pij function, which is a candidate for constructing a Markov chain on this collection of nodes. And this is then what we will call the network random walk transition matrix. So each such network can be endowed with a natural random walk, which is a random walk on the nodes, and which at a certain node makes a random choice where to jump in the next moment according to the conductance to the relative target points. So in other words, an electrical network walker jumps from a node I to a neighboring point j with a probability that is proportional to the conductance between these 2 points. That's exactly this Pij function. Okay, so we have a natural random walk, or Markov chain, as we say, on a network. And the following result shows that this is actually quite often the case, that we can interpret a random walk or a Markov chain on an arbitrary collection of states, in fact, as an electrical network random walk, if we have an additional property that this corresponding abstract Markov chain is in fact reversible. And that's the concept that we shall introduce now. We say that a lambda p Markov chain on a general state space, which is countable, is reversible if the finite dimensional distributions of this process are invariant under time reflection, which means the following. So if I observe a certain terminal time t, or if I fix a certain terminal time t, and I want to observe the Markov process, or the joint realization of the first t realization of this Markov process, so in other words, I look at the statistics of the trajectories up to time point t, then the corresponding law on the, in this case, t plus one-fold Cartesian product of the state space is the same as if I consider the law which is obtained by time inflection. So I observe xt first, then xt minus 1, and so forth. This is again produces a probability law or probability distribution on this t plus one-fold power of the state space S, and I want that these two laws coincide. Intuitively, this means that I can reverse the time and the statistics of the process will not change when I do so. If that's the case, then I call this Markov process, or this Markov chain, reversible. Now we have a little lemma which characterizes the reversibility of a lambda p Markov chain in terms of the two data lambda and p, namely a Markov chain is reversible if and only if for all pairs ij we have the relation that lambda I pij is lambda j pji. This is the so-called detailed balance condition. A detailed balance condition is a condition which is checked on a couple lambda and p, on a couple of an initial law and a transition matrix P, and if this relation is satisfied for all pairs I and G, then we say that the detailed balance condition is fulfilled. And the statement of this proposition is that a lambda P Markov chain is reversible with respect to this time inflection that we have just discussed, if and only if the pair lambda and p, which characterize the statistics of this Markov process, that satisfies this detailed balance condition. This is in fact a simple exercise, and we put it on the sheet to check that this is true. Okay. Now, if we do have, in fact, a transition matrix P for the network random walk, and if we put Pi to be Ci, then by the very construction of a Pij, the detailed balance condition is immediately satisfied, and therefore a random walk in network, an electrical network random walk, if we start with an invariant distribution which is given by these Ci's, then this is in fact a reversible Markov chain. However, one should know that this collection of Ci's is not necessarily summable. So the detailed balance condition can of course be formulated for an arbitrary vector lambda and p. So we could extend this definition of detailed balance condition also to general vectors lambda, which are not necessarily summable. But and this is the case here, so we are not necessarily in a summable situation. But what we can say is that this measure, which we can define through putting lambda I equals pi equals ci, is an invariant measure, because the detailed balance condition directly implies that this vector lambda is an eigenstate for the adjoint matrix P star, then in this case with eigenvalue 1. So in particular, if we do have a lambda vector or in measure on the states which satisfies the detailed balance condition, then in particular this measure is also an invariant measure for the corresponding transition matrix. And in fact, whenever we have such a lambda I Pij situation, then we can define simply Cij, if we have now in this situation of a reversible Markov chain, or in the situation of a detailed balance condition for a pair lambda and pi, then we can also define Cij. A posteriori, we could define Cij basically exactly like this, lambda I Pij. And this would create a network structure on the state space S, and therefore we can basically say that the detailed balance condition is equivalent to the situation that we have an electrical network random walk. Okay, the subsequent little bit of theory that we shall demonstrate in the context of these electrical network random walks also involves a little bit of analysis and a little bit of functional analysis. And for that purpose, we will introduce again these operators, these matrices, but we will understand them as certain operators which act on certain function spaces. So here's the first of those kind of analytical little results. So let P the corresponding transition matrix of a electrical network random walk, and let be lambda the corresponding invariant measure, which is in detailed balance. Then we can introduce the corresponding space of square integrable functions, which are then square integrable with respect to this invariant measure. So here lambda is the invariant measure that is in detailed balance with the transition matrix P, and we will talk about L2 lambda, so this will be the space of summable functions defined on the collection of states of this network, which are square integrable or square summable with respect to the weighted measure, the weighted counting measure where lambda is the weight, so in other words is the integral effectively of this function, of the square of this function, when integrated with respect to the lambda measure. This will be my L2 space that I shall work with. And the claim here is that this operator P, which is the transition matrix, is a symmetric bounded operator from this L2 space into itself. In fact, with operator norm less or equal to 1. Okay, let us first check the symmetry condition on the subset of functions which are finitely supported. So let f be an arbitrary L2 function, and let g be a function which is finitely supported. In other words, g is the same as if we multiply g with an indicator function on a subset A, where the subset A is a finite cardinality. This is done in order to guarantee that the corresponding sums that we're dealing with in the next few lines are in fact finite and well defined. So we don't have to be concerned about the summability. Okay, so then I take the inner product of the application of P to F with the function G, the inner product in this weighted space. So the application of P to the vector F produces in each state I the vector P I J F J, where the sum is taken over the vector J, and this is then as a function in I multiplied with the test function G at position I, and then again multiplied with this invariant measure lambda at position I. So that's just writing out what this thing on the left hand side is meant to be. And here we see that we have this product of Pij lambda I, but by the detailed balance condition this can also be written as a lambda j Pji, where we do not change the summons. And what we see here is that this is just the inner product with respect to the weighted measure lambda of f with the application of P to the vector G. So in fact, this is the symmetry of the operator P on this weighted L2 space, at least when one of the two functions which are appearing in this inner product is finitely supported. We will now convince ourselves that this operator is in fact a continuous mapping from L2 of lambda into itself. In fact, it will be a mapping with operator norm L less or equal to 1. So we take an arbitrary function in L2 and apply P and compute its norm squared. So that's the application of P to the G function. Then we have to square. And by Jensen's inequality, which we apply to the probability measure, which is the probability measure on the collection of states, with regards to this second parameter j in the matrices Pij, if we fix the first state I, then this square of this mean value is estimated from above by the corresponding mean value of the square. And what we see here is that we can take out the summation with respect to the j variable now out of this double sum, have gij squared alone, multiplied by the sum, the inner sum, which is the sum over the I parameter for fixed j of Pij lambda I. But we know that lambda is in detailed balance with P, which in particular implies that lambda is in invariant measure. So therefore this Pij lambda I, if we sum with respect to I, is nothing but lambda j. And we see that the L2 norm squared of the G function alone is appearing. So in fact, the application of P leads a function, or gives a function, which in L2 norm is less or equal to the initial function that we started with. And here in this argument I had a misprint because I need to write the square, of course, here. Okay, so therefore this operator P is a continuous mapping, and by a simple approximation we find that this equality star, which was our starting point for the symmetry, is true for any function f and g which are in this L2 space. So hence the claim of the little proposition is proved. It's a symmetric operator, which is in fact a contraction. Okay, so another important object which we shall now introduce, and which we introduced already before, is the operator P minus identity, which we sometimes call the generator of this random walk on this Markov chain on the network. And sometimes this is also called the graph Laplacian, because it has a lot of similarities with the Laplace operator that we know from mathematical physics, for instance, in which here in our case can be thought of as a discretized version of the continuum Laplace operator. And I hope that this will be clear in the course of the subsequent elaborations. Okay. We now introduce what we call the energy of a function, which is induced from this symmetric operator P or the symmetric operator L. Namely, if we have a function u, we define as the energy of u to be the inner product of the negative of L applied to u with u again in the inner product of this L2 space, which we have just introduced. So that's the definition. The claim is that this has this intuitive of this very nice representation, that it's just the norm squared of the differences of these functions u on all pairs I and j of the state space, where we take the square, not the plane square, but the square again with respect to this Pij lambda j product, which in the electric network case we also write or can write as this Cij as simply the conductance between I and j of the wire which connects state I with j. So this inner product of a function u with the result of the L operator acting on u in its negative form. This is what we call the energy, and this energy has this representation. Okay, why is this representation correct? Okay, we write out the definition of L, which is this one. So it's the mean value of u, which we evaluate at I, where we take the mean value with respect to the transition probabilities when we start from I, and we subtract from this mean value the actual value of the function u at I. So that's exactly L of u, what we have here inside the bracket, when we evaluate this at I. Now, according to the definition above of this E, even with a minus, but basically according to that definition, we have to multiply this thing in the inner product sense with u itself in this weighted L2 space, which therefore we write as the sum with respect to the I variable, where Lu of I is appearing, u of I, and lambda of I. Okay. Now we write this sum as twice half of the sum. Okay, so this is 1/2 of this sum, and we get the same sum, of course, as the second summand with the factor 1/2 in front. But since this definition that we used here for u, I, and j is obviously should not depend on the choice of I and j indices, I can write down the same expression also with interchanging I and j as the names for the two indices over which I take the sum. This would yield a ui minus uj, and here I would have a uj, that's just the expression which I obtained by interchanging the index names I and j, and I would obtain a p ji lambda j. But since I have the detailed balance condition, I can replace the pji lambda j by pij lambda I. This is what I did here. So here in this decomposition, I did two steps in one go, namely I interchanged the indices I and j, and then I used the detailed balance condition in order to write this. And what I do have now is pij lambda I as one factor, and I can just compare that I have this difference appearing twice, but with a different sign, and the other factor is ui and uj, and if I put these two things together, I get a uj minus ui, which is the one common factor, and then the difference of the two other factors with a minus here in front, if I do the algebra right. And I see that this is exactly the expression that I had claimed here for the energy as an alternative representation of the energy. So this computation here is elementary, and it tells me that this operator L or minus L corresponds or can be written in this appealing symmetric form. Again, it's particularly appealing if I replace this pij lambda j expression as I can in the electrical network case by the conductance between the nodes I and j. So from now on, as we basically already did, I want to consider always this detailed balance situation, which is more or less equivalent to the case that we are dealing with an electrical network, where Cij is the interpretation of a conductance, which can be obtained from a lambda p Markov chain in detailed balance by putting lambda I pij as the definition of Cij, or the other way around. If I start from a conductance function Cij, I can introduce a pij through this normalization with respect to each of the starting points I, and then the lambda I, the invariant measure, which is in detailed balance with this pij, is then given by Ci. So depending on my concrete situation in which I want to do computations, I will either use this representation or the other one. Okay. We will then say that a function on the collection of states, which is, say, for instance, also square integrable or so, is harmonic on a subset A of states if the L operator applied to that function equals 0 on that set A. And if you look at the definition of this L operator, it says that the mean value of that function, if we evaluate it on a certain point regarding the possible transitions you can make to the next points for a Markov chain, if you take the mean value of that function relative to that one-step starting point, then this mean value is actually the same as the function value on that midpoint or starting point. This is what it means to be harmonic. And if you had taken a class in PD or something like this, where we consider this, in many cases, the situation when we deal with the Laplace operator, and we call a function harmonic if it satisfies that the Laplacian of the function is 0 in a certain domain, and this is, by the Cauchy integral theorem, if you like, basically equivalent to saying that this function satisfies locally a mean value property. And this mean value property is exactly described in our discrete, spatially discrete case of a graph Laplacian by saying that LU is not. Okay, and then we have the following proposition, which we had discussed already in the past when we were introducing Markov chains and, for instance, the strong Markov property. And we can say that a function u, if it solves the Dirichlet problem, okay, we say that the function u solves the Dirichlet problem, which is of the type that it is harmonic on a certain subset of states A, and it coincides with a certain function f on the complement of A, then we say that the function u solves this given Dirichlet problem, which is given effectively by the collection, or by the tuple of states A, where the function is supposed to be harmonic, and the function f, on which defines the values of this function u on the complement of A. So the Dirichlet problem is given by this tuple of sets, of a set and a function, which in a way is the boundary value. And if P, if the matrix, the transition matrix with which we want to deal is irreducible, then a solution to this Dirichlet problem is unique. And by the way, the function P of correction, the transition matrix is irreducible, as it is intuitively obvious, and you can easily show that as a little exercise. Our transition matrix P, if it comes from an electric network, which is the case we want to discuss here, in this case, the transition matrix P is irreducible if and only if the corresponding graph of edges, which are edges with finite resistance or positive conductance, if this graph is connected. This is the same as saying that the matrix P is irreducible. Okay, if we have irreducibility and detailed balance, that's what's claimed here, then the solution to this Dirichlet problem is unique. Why is this true? Well, if we have two such functions, then we can consider the difference of these two functions. And by linearity of this operator L, we see that this function V, again I'm having a misprint here, the function V is then zero on the set A, because each of the individual components of the functions u1 and u2 each were harmonic, so also the difference is harmonic on the same set. And moreover, on the complement of the set A, this difference function u, which should have the name v in our case, is the zero function. So the difference function here is again harmonic, and it has, if you like, boundary value 0 on the complement of A. And if we insert this function now into the energy function that we had just defined, then we compute the energy, and here I should write a minus. So if I compute now the energy of such a function v, which was obtained as the difference of two solutions to this Dirichlet problem, then I can take this inner product of minus L with this function v. I can decompose this inner product into an inner product which is restricted to the sets, to the collection of states in A, and the inner product which is taken with respect to the states which are in A complement. Now, on A, or I can also, the indicator here, I can move the indicator towards the other side in this inner product because it doesn't change the inner product here. And here I'm just keeping the indicator here. So, and if I do now evaluate this L function, L of V on the subset A, from the fact that L V on A is 0, I'm doing effectively the inner product of the 0 function with the V function, which is obviously 0. And for the second summand, I find that on the complement of A, the V function is the 0th function, so therefore this inner product is 0. And hence the energy of this function is 0. But on the other hand, I had a representation of the energy of the other function, I had another representation of the energy of this function, which was given through this difference values of the difference of the values of the function v at the different nodes of the network. And this appeared here in squares. And so this tells me that all vertices, since this is 0, this tells me that the values of the function v on all nodes which are connected by a vertex must have the same value, but since the graph is connected, I find that the function v must be entirely constant. The function is constant, therefore, all over the place, and since it was constant on a complement, it must be 0 everywhere. So hence, we have uniqueness of the solution to the Dirichlet problem. And here again the remark, the Markov chain here that we're dealing with, this network, random walk, is irreducible if and only if the corresponding network, this corresponding electrical network, or the corresponding graph that we obtain from this electrical network is connected. Finally, for instance, in the irreducible case, we have a unique representation of the harmonic functions of solutions of the Dirichlet problem, namely, if we ask for a function u which satisfies the Dirichlet problem, then we know that the function u is given by the expected value of the random walk or Markov chain, which is associated to this transition matrix, which we run until the first moment that the Markov chain hits the set A complement, and we evaluate the boundary function in that point. Then this function, as a function of the starting point where we start the Markov chain, is a harmonic function which satisfies the Dirichlet, this Dirichlet problem. So it's harmonic on A, and on the complement of A, it satisfies the given boundary value constraint. That this is the case was discussed already in the previous lectures. It's a consequence of the strong Markov property, and it's a useful exercise to convince yourself that again that this is actually the case. So here we see for the first time a very interesting and important connection between the solution to this analytic problem of this Dirichlet problem, for this Dirichlet boundary value problem for harmonic functions, and we can see here that we have a probabilistic representation of the solutions to this Dirichlet problem. And another immediate consequence of this representation is what we call is a weak form of the maximum principle, which we can say it as follows: if U is a harmonic function on a certain subset of states, then it will achieve its maximum on the complement of this set. And why is so? Well, it is so because we know that by the previous representation, the function on the interior, on the set where it is harmonic, the function is represented through this as effectively a mean value, which is taken with respect to the hitting distribution of the chain, the mean value of the prescribed function values on the complementary set, on the boundary set, and therefore any function in the interior as the mean value of the functions on the exterior can be no bigger than the biggest point on the exterior. This is the reason why the maximum of this function is necessarily attained on the complement, because in the interior of A, all possible functions that show up will be some ways of mean values of the function which we have on the complement. But we will not use this maximum principle here in the subsequent considerations. This little corollary here was just meant to show you that you get a nice analytic result at zero cost, if you like, as a consequence of this probabilistic representation. Take a step now towards actual connection to, if you like, electrical currents and voltage concepts on such electrical networks. For that concept, for that purpose, we introduced the notion of a flux or a flow. A flux or a flow, I shall say flux, on the collection of states is an anti-symmetric function on the sets of pairs, on the set of pairs of points which are connected in this network, or connected in the graph of this. In the graph of this electrical network. And being an anti-symmetric function means that the flux on the pair ij is the negative of the flux of the pair ji, and we want to interpret as the quantity I of ij as the actual flux of, say, electrical current, or which is flowing through the edge which connects node I with node j. So of course this flux has an orientation, and this orientation of the flux is represented by the fact that the corresponding flux function, the corresponding mathematical flux function, is antisymmetric. So I of I and j is the amount of, say, electrical charge that is flowing through the edge connecting node I with node j in 1 unit of time. And correspondingly, the flux that goes in inverse direction should be the negative of the corresponding flux in forward direction. Now, if we fix an initial point, an initial node I, and we take the sum over all fluxes into other states j, which are neighboring states in the corresponding graph, then this has the interpretation as the net outflow of the net outflow, which is described by this flux function, outflow from the node I. And if the net outflow of the node I is positive, then we say that the node I is a source of electrical charge. And if this corresponding net outflow has a negative sign, then we say that this corresponding node is a sink of electrical charge. And for such a flux function on the collection of states, we define its energy as the following quantity. It's the sum over all square values of the fluxes on nodes which are connected through a wire, which then is multiplied by the resistance of the corresponding wire which connects the node I to j. And for a function on the collection of states, we define the gradient of this function to be the flux which is induced by u if we interpret u as a voltage function, namely u of j minus u of I. That would be the voltage drop between the two different states I and j, and we want that the flux, the electrical flux, goes in the direction of a negative of decreasing voltage, which means that the electrical charge prefers states with less electrical potential, which is encoded by this voltage function u. But by Ohm's law, the actual voltage drop does not directly translate into the actual electrical current. We have to multiply this with the resistance, which is the same as dividing by the corresponding conductance in order to obtain actually an electrical flux in this case. And in this case, we see that the energy which we had just introduced, namely the energy of a function from L2, is the same as the corresponding flux of the induced electrical network flow, which is induced from this gradient construction, from this gradient flux. So the energy of a function, therefore, this is the energy which we had just introduced, in fact coincides with the energy that we have just now introduced, the energy of an electrical flux. Why is, by the way, this choice of an energy for a flux reasonable? Well, it is in consistency with our physical idea that that the actual power of an electrical current is described by the product of voltage times electrical current. And if we insert Ohm's law, we see that this is resistance times electrical current squared, but the resistance is the same as 1 over conductance. So therefore, this expression that we have here fits perfectly to our physical interpretation, or to the physical definition of the power, which is so the work that is invested in one moment of time by an electrical current which is flowing through the wire from I to J. It is namely the amount of electrical charge squared divided by the divided by the conductance of that wire. So therefore, this definition of an electrical energy associated to an electrical flux is physical. And now comes the main, if you like, technical definition of today's lecture, which is the definition of an effective resistance between two states. So if two states, for instance, are far apart in my electrical network, so I have, let me draw it again, I have an electrical network which consists of many wires and nodes of different charges, of different conductances and so forth. And I have two nodes, I and J, which are, for instance, far apart. I could hook up a battery to node I and a battery and a negative minus pole to node I and a plus pole to node J. And I could ask myself, what's the effective resistance that the network puts up if I consider the whole network as one electric conductor? So what would be the corresponding effective resistance which would replace this whole electrical network if I look on the network as only a conducting device that is installed between node I and node J? And the effective resistance Rij is exactly this quantity which is supposed to describe this. And I want to use the following definition, namely the effective conductance, the effective resistance between two nodes I and J in the network is defined as the minimal electric energy that needs to be invested in order to generate an electrical flux which has only one source, namely a source in I, and one sink in J of size 1 each. So I want to generate an electrical flux, that's my constraint, that forwards 1 unit of electrical charge per second from node I to node J in net. While it is doing it, the electrical charge can be distributed across the entire network through an electrical flux, which can be chosen in arbitrary fashion. However, it is said this should be designed in such a fashion that I have no charge being produced or consumed anywhere else except then in states I and J. And so my effective resistance, again, let me say it again, is defined as the minimal electrical energy among all fluxes, among all possible flux functions, which have exactly one sink of strength 1 in position I and one source of strength 1 in position I and one source in position J of strength 1. The minimal electric energy is what I want to define as the effective resistance. If you look again at these two equations that we know from physics about the power of an electrical current, which is floating or flowing through a wire with conductance C, this definition of effective resistance is again consistent. Namely, as a matter of fact, we consider here the case when the total flow is determined or is defined to be exactly 1. So the I square here is just the 1, and therefore in this case we have that the corresponding electrical power should be equal to the inverse of the effective conductance, which is the effective resistance of the states I and J. So again, therefore, this idea of minimizing an electrical current, where minimizing the electrical energy among all fluxes which generate the given net total flux between node I and J on the entire network, is consistent with our physical idea about resistance. And here's now an analytic result which will help us to actually take advantage of this concept and to connect this with an interesting probabilistic representation that will be useful a little later on. Here it comes. So suppose for a minute that my electrical network has in fact only finitely many nodes. Then we find a function phi star which is unique up to an additive constant, such that this effective resistance between state I and J can be represented as the energy of exactly this function phi star. And moreover, this function phi star satisfies the following analytic equation, namely if I apply the operator L to the function phi star, then it is effectively 0 everywhere except in the states I and J. Yeah, and in state I, the generator L applied to phi star has the value 1 over Ci, and at location J, the value of the generator L applied to phi star is minus 1 over Cj. And this is the analytic condition that this phi star needs to satisfy, and using this I can convince myself that the effective resistance between these two states is therefore given by the difference of this of the values of this phi star function on these two locations I and j. So what this says is the following, that there is a potential function phi star which is uniquely determined up to an additive constant by a certain analytic property, namely that it is harmonic everywhere except in the source and in the sink, where in the source and the sink we have prescribed values for this potential, or for the harmonic operator applied to this potential. And the effective resistance between these two nodes is given by exactly this voltage drop, or by the drop of the potential function when evaluated in the two respective states I and j. Okay, we want to prove this now, and we start out with considering the corresponding variational problem. So effectively what we here study in the definition of Rij is a variational problem. We have a certain set of electrical currents, or correction, a certain set of electrical fluxes, which need to satisfy a certain boundary constraint, if you like, a certain linear constraint, and we want to minimize a certain quadratic form on this. So that's a variational problem. And we convince ourselves first that this collection of fluxes is non-empty because we have a connected network, so therefore there's at least one path which is given as a sequence of states, which connects the state I, or the node I, with the node j, and we can send exactly 1 unit of electrical charge per time through this sequence of connected nodes, which is then one instance of such a flux, which we describe through these conditions here. So therefore the set over which we want to find a minimizer of the energy is not empty. And then so this is effectively a quadratic function on an affine set which has a minimizer. And since it is in a quadratic function, the minimizer needs to satisfy the corresponding first order Euler-Lagrange equation for this variational problem, which in our case says that the energy inner product, if you like, of the critical minimizer with any other flux, which is just a flux then which needs to satisfy only which needs to be a flux which has no net source or no net sink, that this inner product needs to be zero. That's the first order condition which follows directly from the definition of the variation problem which we want to solve. So if we have a minimizer of this variation problem, then the corresponding quadratic form, and then it's a critical point for the corresponding linear form, which is the first order derivative. And that's expressed by this inner product here. Now, if we take a closed loop in state space, S, and we define a flux, a circular flux along this closed loop of states in state space, so therefore we define exactly this flux function which assigns just values +1 to each of those sequence of nodes or sequence of edges which we observe along such a closed sequence of nodes in the network. Then we can use this test flux in this inner product, and then it's easy to see that just as in the case that you know from the situation of functions who have of vector fields which are of divergence 0, that this correction of vector fields who have rotation 0, that this must be in fact gradient vector fields, we can show from this property that if we define a phi star function as follows, and we set phi star to be equal 1 at position I, and then for any other position in state space, we define the phi star function as the weighted sum of all these increments, as we will interpret them now, of this critical flux multiplied by these conductances for any path which connects the initial state with the state k. And this is a function which is well defined. So again, we have a state I, or say preferred initial state I, where all the fluxes are starting from, and now we want to define a function phi star as follows. We define phi star at that location I to be equal 1, and for any arbitrary point in state space k, we define phi star of k as the sum of all these flux values along the edges that we observe if we take any path gamma of connected nodes in the network. Gamma is such a path here. So we take the sum over all these flux values on these along these edges in the graph, but we multiply this sum of edge values also each time with the corresponding conductance related to that edge. So in a way, we sum up all the energies that we pile up as we go along. And the fact that this I star function, this flux function, is orthogonal in this inner product with respect to all circles, means that if I had chosen another path gamma tilde, then this effectively creates, by concatenation with the inverse other path, a closed path, which then tells us that this inner product is independent, effectively, or that this sequence of sums is independent with respect to the chosen path, and therefore this function phi star in total is well defined. Now, if we compute the gradient of this function in the sense that we had discussed above, namely we take just the difference of this flux, we take the difference of this phi function on two connected nodes and divide by the corresponding conductance. Then by the very definition of this I star, by the phi star through the I star, we see that the gradient of phi star on such a pair of nodes is nothing but the I star divided by the corresponding conductance of that edge. And in particular, we see that the energy of that function, in the sense of the energy of functions that we had introduced before, is exactly equal to the energy of this critical flux. So we have managed to define a function phi star which has the same energy and whose as this critical flux I star, and the flux I star is in fact the gradient flux of the function phi star. So therefore phi star is really the potential for this flux, as we would say. And then we can also evaluate the Laplacian operator on this function, or the graph Laplacian on this function phi star in an arbitrary location k. Then this will be, by definition and by what we had just said, this gradient of the function multiplied by the corresponding transition probability minus 1. This is exactly this weighted difference value that we had observed in the definition of this L operator. And we see that there is this cancellation of the conductivity of the edge that connects k and k prime. So in the end, we end up with the sum of all the flux values for fixed initial position K in the network. That's the position where we wanted to evaluate the Laplace operator. And since I star is a flux which belongs to this collection of flux functions on which we wanted to take the minimal value, we know that this has only two locations, K, where this is different from zero anyway, namely it is, this first sum here is just 1 when K happens to be the source of the flux, which is the position I, and it is minus 1 when this K location happens to be the sink of this flux, which was location J, where it is a minus 1. So therefore, these two values appear. And finally, not quite finally, but this, we want to remark that this phi function is uniquely defined, in fact, up to an additive constant, because if we have two such functions, then since the function have the same prescription on the result under L, in just these indicators with these weight factors 1 over Ci or 1 over Cj, therefore the difference of the two, any two such functions, phi star and phi star bar, would be harmonic everywhere, and by the same argument as before, which is effectively this integration by parts formula, we would find that these two functions can differ only from each other by a fixed constant. Right, and finally, if we want to evaluate now the effective resistance, since we know that the energy of this I star flux is the same as the energy of the phi function, we can now apply our integration by parts formula, which gave us a representation of this energy in terms of the graph Laplacian L. And the graph Laplacian, as we had just said, sen of this phi star function has only two contributions where it's non-zero, namely it may be plus or minus 1 over Ci or 1 over Cj. So therefore this inner product, which is effectively a sum over all states, has only two summands which are non-zero, namely the summand corresponding to state I and state j, where by the definition, by the property that we just had here, is just phi j minus phi I, because we get a one function, a 1 on each of these two states with the weights 1 over Ci and 1 over Cj, but this is exactly compensated by the definition of the L2 inner product. So therefore, this formula is obtained. So let me sum up what we have just found so far. So we have seen that if we want to find the minimal flux, which associates, which has exactly one source in location I of strength 1, and correspondingly one sink of strength 1 in location J, which is of minimal energy, then we find that this minimal energy flux must necessarily be a gradient flux. And this gradient, or the function phi star, which is unique up to an additive constant, is what we call the potential function for this electrical flux. So if we think that only those fluxes are physically reasonable, which minimize a certain energy, then we can say that there is a unique physical or electrical flux which is determined by being the gradient flux of a uniquely determined potential function. And the effective resistance between these two nodes I and J is then just the difference of the voltage difference of the corresponding electrical field, which is the electrical field induced from the potential function phi star. So all this is very physical. And finally, we also have a very nice probabilistic representation of this effective resistance in terms of this network random walk. And we can now say that this effective resistance can also be interpreted as the inverse of the probability for the electrical network random walk, which starts in node I, where we evaluate the probability that this walk hits the state J before it returns in the strict sense to the state I, multiplied by the total conductivity of the state I in the denominator. So the effective resistance between two states, I and J, is the inverse of the product of the total conductivity of the state I multiplied with the probability that the random walk, the electrical network random walk, when starting in I, hits the state J first before a strict return to state I. Okay, and why is this true? Well, this is true because of the following. So we know that this effective resistance can be obtained by taking the difference of the potential at the two different nodes on which we want to compute the effective resistance. And since this function phi star is uniquely determined up to an additive constant by an analytic condition which is related to the network Laplacian applied to the function phi star, we can assume without loss of generality and without changing the actual value of Rij by just applying an appropriate shift to the function phi star, that phi star in J is just 0, so therefore this difference here is effectively only the negative value of the potential function at position I. Now this phi star, all of those phi star functions which can appear there will be solutions to this network Laplacian equation, which in particular implies that the function phi star is harmonic on all states except I and J, because then these indicator functions give a 0, so which means that the function phi star is harmonic. Moreover, we want that phi star of J is 0. Now we know that harmonic functions which have defined values except at certain locations, these are effectively those functions which satisfy a Dirichlet problem. And by uniqueness of the solutions of the Dirichlet problem, we know that phi star of Z as a function in the states Z must be a constant multiple of the function which associates to every Z the probability of hitting I before hitting J. So this thing here, this function here, which I write here as a function in Z, is a harmonic function which has value 0 at position J by the strong Markov property again, or by the Markov property in this case only. And therefore, it must be a linear combination or linear dependent on the actual function that we're looking for, just by uniqueness of harmonic functions. And the only thing that we need to determine in order to have the full information about the function phi star is the value A. What's the constant A? In order to determine A, I recall that I have a requirement on the network Laplacian applied to the function phi star at location I, because it is required here to have the value 1 over Ci. Now if I apply the network Laplacian to this hitting time probability, which is what I do here, and evaluate the whole thing in I, just by the definition of the network Laplacian, I obtain that this is the average value of the pk values when k is a neighbor to this starting state I. I need to multiply with pik, and then I have to subtract the value of the function p dot in when dot equals 1, which is p of I, of tau I being less than 2 tau j, which is just the 1 function. So that's just the network Laplacian applied to this function when I evaluate the whole thing in location I. But what I see here is basically the probability to hit state I before state j, where through this one time step shift, which is effectively applied here using the Markov property, is then evaluated only on the trajectories which I feed into the evaluation functional for the hitting times after the first time step of evaluation. So in other words, this Laplacian here is the same probability that I'm dealing with at position I, except for that there's a one-step shift on the paths, which means that here I'm dealing effectively with the strong hitting times and not with the hitting times themselves. But this is then hit by the -1, which came from the identity operation. So therefore, this is just minus the probability of the corresponding adjoint event, which means that this is the probability that I start in I to meet the state j before I have a strict return to I. Because this is just the probability of the corresponding complement event. So this then is the evaluation of this network Laplacian on this hitting time or hitting probability as a function of initial start. And since this times A is required to be 1 over Ca, I find that A is in fact -1 over this whole expression here on the right hand side, which then if I put this into the actual definition of the function phi star and evaluate this at location I, at location z equals I, gives me exactly the presentation of the expression that was in the claim. So we obtain a nice probabilistic representation for the effective resistance of a potentially very complicated electrical network, for the effective resistance in a potentially very complicated network through the corresponding network random walk. And sometimes if you want to simplify networks and replace a network by a simple wire, then you can sometimes use this probabilistic representation in order to so we can generalize this whole consideration, for instance, to the case when we want to compute the effective resistance not between individual states but also between collection of states. So for instance, we could talk about the effective resistance between a single state I and a collection of states A, which in a similar fashion as before is defined as the minimal electric energy that is needed to create a flux which has total source or has sources, only one source of size exactly 1 in location I, and which distributes the electrical charge only to locations inside the set of nodes A, where the total amount that is delivered to the total amount of charge per unit of time that is delivered to the set A is -1. That would be a proper definition for the effective resistance between an initial state I and a collection of states A. And by very similar arguments as in the case above, we can find that the effective resistance for this collection of sets is given by the inverse of this total conductance of the state I multiplied by the probability that when I start the random network walk in location I hit the set A before I do a strict return to state I. And the proof goes in just the same fashion as before when the set A is just single valued. Okay, this is all very nice and shows a nice way to represent certain engineering quantities through network random walks, and this can be used sometimes in order to obtain an intuitive picture about what is actually really going on in the network. It sometimes also helps to get an intuition of how you should replace a certain electrical network by a simpler fashion which behaves in a similar fashion, or it could also give you some intuition of how you can change an electrical network in order to achieve this or that performance goal. But it can also be used in the other way around in order to learn something for the corresponding random walk or Markov chain on the network by applying engineering thinking, if you like, or engineering ideas to the corresponding electrical network. So, and we want to do this now in the case that we are actually dealing with an infinite network. And here we want to come back to the question of recurrence and transience. And I want to present to you as final theorem in this collection of results, and as a final theorem on our final theorem of our series on Markov chains, I want to give you a nice result about the connection between recurrence and transience and the existence of what is called an infinite flux, or a non-trivial flux with finite energy. Okay, so now consider the case now that the network is infinite, which means that we really have an uncountable correction accountable, but really infinite collection of states. And consider a fixed node I in the collection of states. Then we say that we have a flux from I to infinity if this flux function I is a flux which has only one real source of strength 1, say, in I, and has absolutely no other sources or sinks wherever. So it is something that really distributes 1 unit of charge per 1 unit of time into the network and propagates this 1 unit of charge, but this unit of charge is not consumed at any fixed point. So it is basically consumed at infinity by a collection of points which are infinity, but you cannot fix the actual location where this charge is consumed. And this is called a flux from I to infinity. So let me say it again. A flux from I to infinity is a flux which has one source and no other sources or sinks, and the total source or the total flux at location I is normalized to be 1, say. This is a source. This is a flux from I to infinity. And now, using this concept of a flux from I to infinity, we can formulate a very nice and easy to remember theorem, which says that the network random walk on an infinite network is transient if and only if there exists a non-trivial flux from some state I to infinity, which is of finite energy. So that's the statement. it says that the network random walk, or the network Markov chain is transient if and only if the network is big enough, which is formulated by saying that there exists a way to dissipate, if you like, 1 unit of charge per 1 moment of time to propagate it from 1 to infinity with finite energy. So this means that there are so many different edges in the network that you can distribute this 1 unit of flux that you have to distribute into it, if you feed into the network in such an equilibrium fashion, if you like, in such a weighted and nice balanced fashion, that the total energy is still finite. If this is the case, then the network random walk is transient, and it is exactly in this. If you have such an finite energy flux, then it is exactly transient. If you don't find any of such finite energy flux from I to infinity, then the random walk is recurrent. Okay, how do we prove this? Okay, let us first assume that there is a finite energy flux from I to infinity, and let Sn be a collection or a sequence of subsets of S which are increasing and which exhaust the collection of sets. So it means that the collection of states is increasing in such a fashion that the total union of all these sequences of all these, the union along the sequence of this collection of states is actually the full set S, and assume that at every index n the collection Sn of states is finite. Then I can use this finite energy flux from I to infinity and restrict it effectively to the collection of wires which belong to the set Sn. This is then again of finite energy because the corresponding energy is just smaller. I just need to evaluate less nodes. And the total probability, if I start in node I to hit the complement of the set Sn before I do a real return towards the state I, is, as we know, given by the inverse of Ci times this infimum value, times this effective resistance, which is defined in terms of the infima over all these finite energy fluxes. But this infimum over all these energies is bounded from above, obviously, by any of these possible energies of such fluxes which may appear in this energy competition. And the energy In, which was obtained from the previous energy by restriction, effectively, is one of those competitors. But we know that this energy of In is less or equal than the corresponding energy of the infinite energy flux. So therefore, this inverse ratio is bounded from below by the corresponding inverse ratio of the energy of the flux from I to infinity. But we know that this is a finite energy flux, so therefore this number is bounded strictly away from zero. And as a consequence, if we ask what's the probability of never returning to I in strict form, then this is bounded from below by the limit inferior of the probability to hit the complement of these sets Sn as n tends to infinity, but this quantity has just been bounded by a strictly positive number from below. So therefore we know that the probability of never returning is strictly positive, which by our known dichotomy between transience and recurrence actually means that the random walk X must be transient. So therefore we see that the existence of a finite energy flux from I to infinity entails the transience of the random walk. Conversely, if X is transient, then we can consider the following function, which, if we start at fixing position A, if we start in initial position A, we start a random walk at location A, and we count the number of visits that the random walk does to the state I for all i's, for all states I. This is a function in the state I, and it is then easy to check that this function phi I assumes finitely many values only by the transience of the chain. So therefore it's a well-defined function. We can also easily show by using the Markov property that this function phi is harmonic outside the starting point A. And this means that the corresponding gradient function is a non-trivial energy, is a non-trivial electric flux. And it is left as an exercise to check that this flux has in fact finite energy. So therefore, using the transience of the walk, we were able to construct a non-trivial finite energy flux. So we see that transience of the walk is in fact equivalent to the existence of a finite energy flux. So of course this was only a very quick sketch of the proof of this theorem of Royden-Lyons, which is in this form basically from the 1980s and due to Terry Lyons. It basically tells us that if you want to check for recurrence or transience of a random walk on an electrical network, you have to check whether it's possible to construct at least one of such a finite energy flux from any given state to infinity. So therefore the question about recurrence and transience becomes now very constructive, because you try to find whether it's possible to find such fluxes or not. And one nice example, which I will not discuss in detail, but you might consider to do so, is the following result, which is also in that paper of Lyons, where he discussed this criterion, which we had just demonstrated. That's the example of a random walk on a wedge. So a wedge is here in this example is a subset of the three-dimensional lattice. We know that the three-dimensional lattice as a whole is transient by Pouliot's theorem, but we can ask ourselves, is it possible to restrict the three-dimensional lattice in some fashion that in the end we obtain still a recurrent set of states? And what we have to, the corresponding example that we want to discuss here is basically given of the following type. We consider a subset of the positive orthant in three-dimensional space, and we give a function f which depends on the z variable, which in this case is called n. And we have a function which allows us to grow in the x and y direction up to a level f of n with the x and y coordinates. So in some way we have something like a subgraph of the function f, if we consider this as a function in two variables. And so what we obtain is a wedge which can grow in the direction, I should have drawn it probably differently, which can grow in each of the directions x and y as given by the function f in the z direction. So in the situation that n is 2 instead of 3, the corresponding picture is easier to draw. You have a function f which has any type of shape. You draw this as a function in this variable n, as a graph over the n axis, and then the collection of all admissible points in this case two-dimensional wedge as a subset of Z2 would be the all lattice points which lie in this interior. So that's something like a generalization of a linear wedge, and the shape of this wedge, which we obtain in Z3, would be slightly more complicated because it has also a Z or a Y component, which is then in this other fashion. So this shape of this generalized wedge is, of course, very strongly determined by the given function n. So if n is growing very quickly, then this wedge will be almost like the full simplex wedge of the positive of the three-dimensional positive first orthant. And the finding here is that the nearest neighbor random walk, so the simple random walk, which is an instance of an electrical network random walk when we work with conductance 1 throughout, then this simple random walk on the corresponding wedge will be recurrent if and only if this sum of inverse values of the function f squared is summable. So what does this say? So if the function, is infinite, if the function f is growing very quickly, then this sum here will be finite. And this sum being finite then corresponds to the transient case, which is the opposite of this, which means that the graph is so big, or the lattice that we obtain is so big, that it will become a transient random walk. But if the growth of the function f is very slow, then this sum here will be infinite, and this corresponds to the case that the corresponding wedge is relatively small, and this corresponds exactly to the recurrent case. So that's a nice example in two aspects. Namely, first, it's a nice example where the effectiveness of this method can nicely be demonstrated by just showing that there is finite energy fluxes from a fixed state to infinity. So the method can nicely be applied to show this result. And secondly, it is an interesting result regarding its actual conclusion, because it says that whether or not a certain sublattice of three-dimensional space is recurrent or not can be really described or can really be determined by the precise growth of this lattice. And we therefore have, if you like, some intermediate regime that is not covered by the Polya result, which is strict in the sense that it's something that's in transition between 2 and 3 dimension. Here we have something that interpolates between random walk behavior of 2 and 3 dimensions. And it can be proved, as I just said, by applying this finite energy flux method that we had discussed. Okay, so this concludes our whole segment of Markov chains. And I thank you for your patience with this. I hope you liked at least some insights here, how you can connect Markov chains with electrical network theory, and this, on the other hand, feeds back nicely to the theory of Markov chains if you adopt this electrical network thinking, because it will help you to show transients and recurrence in a very efficient manner. Okay, this is the end of our segment on Markov chains, and we will then now make a big step towards a new class of stochastic processes, which is martingales, and so we will have a new start, if you like, within our lectures on Markov chains and on stochastic processes in general.